we present TexMesh, a novel approach to reconstruct detailed human meshes with high-resolution full-body texture from RGB-D video, enabling high-quality free viewpoint rendering. Our model takes an RGB video, a corresponding environment map, and a per-frame coarse mesh as inputs, and produces a per-frame fine mesh and a high-resolution texture shared across the whole video. The coarse mesh is a parametric human model obtained by 3D tracking from an RGB-D camera. Depth is used only for creating the coarse mesh. Previous human reconstruction methods often generate the rough shape of the actor but misses some of the geometric details and often hallucinates incorrect deformation in occluded parts. The texture often includes baked-in lighting and is blurry due to small geometric misalignments. To address these issues, we introduce TexMesh, a novel framework to reconstruct both significantly higher quality mesh and textures from a real-world video. In this example, our result resolves these problems and shows correct jacket deformation and texture. Our framework consists of 3 modules: albedo and normal estimation, texture generation, and mesh refinement. Albedo and normal estimation takes an RGB image and spherical harmonics lighting and estimates texture and geometry information in the form of albedo and normal images. Texture generation selects key albedo frames and generates a high-resolution texture map from them. Mesh refinement takes a coarse mesh from RGB-D tracking and the normal image and estimates a refined mesh. The training has 2 stages. In the first stage, we train albedo and normal estimation and mesh refinement on synthetic images with ground truth supervision. In the second stage, we adapt texture generation and mesh refinement modules to a short clip of the real video, using self-supervision. Finally, we infer on the whole video at interactive frame rate. The target of albedo and normal estimation module is to separate texture and geometry information. The albedo is the key to estimate clear texture, and the normal is the key to recover detailed geometry. We also include a post-processing method to force the consistency of albedo, normal, and lighting. Texture generation module selects key albedo images based on visibility and converts them into partial textures by sampling. The mesh from pre-trained mesh refinement module provides a correspondence between image space and texture space for sampling. A coarse full texture is constructed by averaging the partial textures with weights. The weights are chosen such that each texel is influenced by a limited number of frames. The texture is then refined by a CNN optimized from scratch for each video. The supervision comes from rasterizing the texture to image space and comparing it with the input albedo images. The small geometric misalignments are resolved by back-propagating gradients to the mesh and thus the mesh refinement module. The mesh refinement module first extracts features from a normal image, then converts those features to UV space. The conversion is done via sampling according to the correspondence between image space and UV space established by the coarse mesh. The UV space features are then sent to a CNN to predict a 3D displacement map. We obtain the fine mesh by adding the displacements to the coarse mesh. This module is first trained using synthetic data with ground truth supervision and later self-adapted to a short real sequence via photometric and temporal losses. In mesh refinement, we proposed a deformation propagation loss to handle occluded regions. To reconstruct a vertex invisible in the current frame, we find the visible counterpart in the set of keyframes and propagate the deformation from it. The comparison shows that the one with propagation has more clothing details. Here are the mesh reconstruction results. We reconstruct spatial temporally consistent detailed meshes, including dynamic clothing deformation. Compared with text-to-shape, our result includes more details and is more temporally consistent. We can reconstruct the occluded parts like the back of the human. In this case, the shorts can be well reconstructed when occluded. We can view the human from different viewpoints. Here are the rendering results. The textured reconstruction enables high-quality rendering, where we can see the clear logo on the shirt. Compared with the baseline, our rendering color is more faithful to the original video. The textures are well recovered for both the front and the back. In this synthetic example, the ECCV text and the closing deformation are well reconstructed. We can also view the human from different viewpoints. The mesh and albedo texture enables relighting application. This is the original lighting. This is the rendering under new lighting. To sum up, we present TexMesh, a state-of-the-art method for high-fidelity human texture and geometry reconstruction, enabling high-quality free viewpoint human rendering or real videos. Our key idea is a self-supervised learning framework to adapt the synthetically trained model to real videos. We will address two limitations in the future. First, we require the lighting to be known. In the future, we will estimate the lighting from the video instead. Second, we assume the deformation in invisible regions is the same as in the keyframes, which is not always correct. This problem could be potentially addressed by combining closing simulation. Thank you for watching.